We've now seen a lot of information about components, how and why they can be used, so we're now going to create and use our first custom component. This will be an actor component that will allow the parent actor to float between 2 points, so something nice and simple, but it will show us the main concepts that we're looking for when working with actor components versus scene components. So before we get started creating our class, we're just going to take a quick tour around the project that you can download to follow along with some pre-made example classes. In the main map, we have a few different actors with the destruction components attached to demonstrate the different outcomes. We also have in the content browser some different effects and a default mesh. And then finally, we have a demo actor blueprint, which is simply a child of the demo actor C++ class. This is just an empty class with an interface attached, ready for us to test how we can add our custom components to later. So we'll be using all of these later in the course, so you don't need to worry about or be concerned with these right now. Just know that they're there, and if you did want to look at them between the different videos, then they are fully implemented and you can take a look at what they're doing, but we will be covering those all in time. So to get started, we can create a new C++ class of type actor component, and notice here there's a quick recap on the difference between the actor and the scene component if we highlight over these. Just mentioning the difference that the actor doesn't have a transform, the scene component does. So we'll be creating a floating movement component that doesn't have a transform of its own, so that we can see how we would use the parent transform in this approach. So select the actor component, ensure that it's in the components folder, and name it something like floating component. Then select create class and wait for this to compile. So inside of the components header, we can leave all of the default functions as we'll be making use of these later. We'll start by adding a couple of public variables. The first is an f vector named float range, which will default to 0 on each axis. This will be the range that we want the actor to move in each direction. And if we add a U property to this, we can easily update and try different ranges in the editor. To make this edit anywhere, I'm also going to make this blueprint read-write just for that added flexibility. And I'm going to place this in a category named floating. Next, create a float named speed multiply, which I'll default to 1. This will be our speed to control the actor's movement. I'm going to also copy the U property from above and paste it just above our float variable, again so that we can easily test the different speeds. And then we can create our final variables in a private section. We won't need these exposed anywhere. The first will be a generic type of a actor named parent, which we can default to be a null pointer. And then another f vector. This one I will name start location, and we'll fill this one on the begin play, so we can leave that here. So over in the code file, one of the first things that we usually need to do when working with components is find some kind of reference to the owning actor or the root component within that class. In this example, we're going to be looking for the parent directly. We can do this in the begin play function, as we won't need the reference before this stage. And we do this by simply setting our parent to be equal to the result of the getOwner function call. This function simply finds whatever the component is attached to, returned as the type of a actor. Then below this, we can start using our parent information. So first we'll check if the parent is valid. Now just a quick note, this shouldn't really be required, as a component can only exist if it's attached to something, and only actors and above in the hierarchy can have a component attached to it. Even when we look at things a bit later, like attaching a scene component to another scene component, that function call is still going to be looking for the actual actor class that the parent component is attached to. So at this stage, if parent is ever returning null, then we have a much larger problem in the project somewhere in our code, but this is something that you'll see a lot in existing code. So we're just going to follow a very similar kind of approach and coding style just here. So now that we're sure that we have our parent actor stored, we can start by setting our start location vector that we created earlier to be the returned value of the parent get actor location. And this will be the location that we return to when we're moving our actor in the tick component function a little bit later. This next step is optional, but something that can be very handy to become familiar with when you're working with components. And what we're doing here is forcing the parent actor's root component's mobility to be movable. So as we know, the entire reason that we'd be placing this component onto an actor is to get it moving, rather than needing the designers to come into the editor and always remember to update the settings per class or even worse per object. We can just override this here in the code so that anything that ever incorporates this component will have the desired mobility settings, thereby avoiding the error and warning messages saying that you're trying to move something that's set to static and things like that. So you can do this in multiple things as well. We can default the physics type. So if we know that something needs to also have some form of physics applied, we can get all of these from the standard actor components. With that done though, if we hop down to the tick component, we can create two new floats, one that I'll name time, which will be equal to the get real-time seconds function, and we'll be using this in a second, constant float named sign, which will be the result of using the fmath sign, multiplying our time by our speed multiplier variable, and this will control the movement between the start and the target endpoint, basically just creating our sine wave so that we'll have that constant movement from point A to point B. And then finally, and the most important thing, is going to be updating the parent's location. Again, we'll implement a check here to ensure that the parent is still valid. And then inside of the if check, we simply set the parent actor location to be between the start location plus the float range multiplied by sign. And of course, ensure to encapsulate the last part of the equation just here, as you can see. And that's it. Everything is now ready to go if we compile. So hit the compile button and get that started in the background. The important takeaway here is that as we're using an actor component, we're making heavy use of the details that we have on our stored parent. So in the begin play, we're getting its initial location and storing this as the starting point. And then in the tick component function, we're constantly updating the parent's location based on the sign calculation and the parent's start location. So with that compiled, if we head back over to the editor, we can now go and test our results. This is going to be really easy by taking any of the existing demo actors in the level. Also note here that the mobility is defaulting to static, and this will be updated in just a moment during play. So with the actor selected, select the Add Component button, find the floating component, and then select it in the hierarchy when you have that one created. We'll just want to change the floating range to something higher than 0. I'll set the play mode to simulate so that I can easily grab and test the new floating actor, and then notice a few things here. So first is that the mobility has successfully been updated to movable, and this has been done at runtime at the begin play function call. And next is that we can easily change any values for the floating range vector and the speed multiplier to get different results during play. So as I'm doing here, you can go around and play with some of those options and just see the kind of results that you can get from this very simple component that hasn't taken us very long to implement, but we can already see how these can be easily applied and reused between different actors. And in fact, we can do that now. So we can also add the same component to another actor. So I'll just leave the play mode here. I'll grab one of the other actors that I have in the level. So this one also has the homing component attached to it, which we'll be looking at a little bit later. But by adding the same component, we can completely customize its movement for different runtime results. So with that done, we've just created our first custom component and seen some of the slight changes in the logic that might be needed when compared to working with the more standard object-derived classes.